Okay, welcome to lecture 9 for Calculus 1. This lecture is going to be about the derivatives of inverse functions. So we're going to talk about inverse function derivatives as well as the logarithmic function derivatives, which we'll see is also actually an inverse. Okay, so in general, an inverse function is written with this sort of notation. So it looks like f with this little -1, but this is not an exponent. This -1 just indicates that this is the inverse of f of x. Okay, so this is just inverse notation. So the inverse function meets the following criteria. Now last time we saw compositions of functions like f of g of x, right? If we input one function within another. So if I were to put f of x inside its own inverse, these functions would undo each other, and I would get back x. And this is true for all x in the domain of the inverse of f of x. Okay, and the same thing holds the other way. So if I put the inverse function of x inside f of x as an input, then that becomes my inner function, f of x is my outer function, I'm going to get back x again. So they undo each other in both ways, or from both directions. And that will be true again for all x in the domain of f of x. Okay? So let's consider f of x is equal to x squared. And let's suppose we'd like to find f prime of 2. So we want to find the value of the slope of the tangent line at 2, 4. Okay? So we start off as we always do. We take our derivative. In this case, it would just be by power rule, right? 2 comes down as a coefficient of x. The exponent becomes 1. If we evaluate f prime of x at x equals 2, we're going to get 2 times 2 is equal to 4. Okay, so far so good. That's straightforward stuff. Let's see what happens with its inverse function. Okay, so to first find the inverse of f of x is equal to x squared, let's consider, first of all, x is greater than or equal to 0. For the sake of simplicity, we're going to talk about later a little bit more why we want to do that. But for now, we'll just consider positive values and 0. So step 1, we want to rewrite this with y in place of f of x. So this is y is equal to x squared. And then we're going to swap the x and the y. Okay, this is our process of finding the inverse function. So we're going to have x is equal to y squared now. And we're going to try to solve this thing for y. Now, in general, I just want to make note. So if we were to take the square root and we truly were trying to solve for y, we would have to make sure we're doing plus or minus the square root. But because of our domain restriction, in this case, we're only going to consider the positive square root of x. Okay. But in general, whenever you have an even power that you're trying to undo, you always want to consider plus and minus. Okay. So therefore, we get this function y is equal to the square root of x. In other words, the inverse function of f of x is equal to the square root of x for all non-negative values of x. Okay, so an additional note, if we wanted to include those negative values, we would also need to consider then the negative square root of x, but we're leaving those out for simplicity. Okay, so now to find the derivative of the inverse function, and we're going to use this notation df with this little -1 over dx, we now simply derive the inverse function of f according to our rules. Okay, so the square root of x can be rewritten as x to the 1/2 power. I've got my domain restriction here as well. We take the derivative, that 1/2 comes down, we subtract 1 from the exponent, derivative x to the 1/2 is 1/2 x to the -1/2 power. Now, let's evaluate the derivative at 4, 2. And no, we started over here with the point 2 comma 4. But when we found the inverse, we swapped x and y. So we're going to do the same thing over here. So we're going to swap that x and y value, and we're going to consider now this other point, 4 comma 2. It's a different point than 2 comma 4. But let's see what happens. There's an interesting pattern that emerges here with inverse functions. Okay. So if we evaluate the derivative of the inverse function at x equals 4, we do our math, 1/2, 4 to the negative 1/2, which is the same thing as 1 over 2 radical 4. 1 over 2 times 2 is 1/4. As a reminder, that was our slope of the tangent line in for f at 2. That was 4. And this has come out to 1/4, the reciprocal of that. Okay, so here's a plot. So we've got y equals x squared, the function in blue. We've got 2 comma 4 plotted here. And we've got the tangent line to this curve at the point x equals 2 with the slope m equals 4. Then in red, we've got the inverse function, y is equal to the square root of x. And at 4 comma 2, right, so this is the point where x and y have been swapped, you've got a tangent line here to the square root of x, and it has the reciprocal slope, where m is equal to 1/4. Okay, so this is a interesting sort of pattern that emerges when you have inverse functions and their derivatives as well. Okay, so their slopes turn out to be reciprocals when we swap those x and y values as well. All right, so it's a quick look at it's an introduction to inverse functions. Now let's talk about the derivative of the natural logarithm. So for all positive real numbers x, the derivative of the natural log of x is defined as 1 over x. Now, the natural log function, if you remember, this is the inverse of e to the x. So if we were to evaluate e to the x inside of the natural log, we would just get back x. And if I placed natural log of x as the exponent of e, again, I would get back x. Okay, so in general, exponential functions and logarithmic functions are inverses. Okay, so derivative of natural log of x is 1 over x. More generally, if we have u, where u is some complex function, this is if we're composite functions, so we're building on chain rule here, the natural log of u, when we derive that, is going to give us u prime over u prime being the derivative of that inner function. All right, let's look at some examples. So example 1, we've got the natural log of 2x. Natural log is our outer function, 2x is our inner function. And if we did this using our old-fashioned chain rule, we take the derivative of the outside. That will lead us to 1 over u, according to this law, u being 2x. We take the derivative of the inside, u prime would be 2. And by chain rule, we would have done f prime of u times u prime, and that would lead us to 1 over 2x times 2, or just 1 over x. Now, in this case, it happened to be 1 over x, but that doesn't mean that's going to happen every single time we have some sort of inner function that's not just x. Okay. So that was just showing you, this is where that rule comes from, u prime over u that we have. That's just where it comes from with chain rule, but in general, you can just skip to that u prime over u. And that's what we'll do over here in this case. So we've got y is equal to natural log of x squared plus 1. U is just x squared plus 1. u prime is 2x, we'll just skip straight to our formula. U prime over u, you're going to get 2x over x squared plus 1. Okay, now we've got an example 3. H of x is equal to x squared times ln of x. You've got two functions which are multiplied by each other. We're going to have to use the product rule. Okay, so we go ahead, we call our x squared a. We call natural log of x b. We can list them both out over here and derive each one individually. So x squared by power rule derives to 2x for a prime. Ln of x, as we just saw, becomes 1 over x for b prime. And then put them together in your product rule fashion. A prime b plus b prime a. 2x times natural log of x, 1 over x times x squared. And we can clean that up a little bit, and we can just simplify that second fraction into just x. So 2x ln x plus x. That is our h prime. Now for number 4, we've got natural log with cosine of x plus 2 as the argument or the input in the natural log. Okay, so we're going to use chain rule here as well. This time u is going to be all of that that's inside cosine of x plus 2. Its derivative will just be negative sign. When we derive 2, it's going to disappear. So we've got u and u prime. Just throw that together with your formula, u prime over u. Negative sine x over cosine x plus 2.